Welcome to Why Math Works. Today, we continue our exploration of non-traditional proofs of traditional inequalities. What happens when a third variable enters the picture? Let's continue our journey into non-traditional proofs of inequalities. In this video, we introduce the idea of two triples of real numbers being of the same type, and we use it to prove an elegant inequalities. When two triples are aligned in the same order, their paired product sum is the largest. We consider two triples of real numbers, the triple A1, A2, A3, and the triple B1, B2, B3. We write them in a table. The first triple goes in the top row, and the second triple goes in the bottom row. Now we define what it means for two triples to be of the same type. The largest number in the top triple must stand above the largest number in the bottom triple. And the second largest number in the top triple must stand above the second largest number in the bottom triple. So the ranking pattern in the two rows must match. For example, the triples are of the same type if A1 is less than or equal to A2, and A2 to A3, and B1 is less than or equal to B2, and B2 to B3. In this case, the order matches in both rows. If we permute both triples in the same way, the type is preserved. For example, A1, A3, A2, and B1, B3, B2. And also A3, A1, A2, and B3, B1, B2 are triples of the same type. Now suppose that A is a positive number, and it is less than or equal to B, and B is less than or equal to C. Then the triples A, B, C, and A squared, B squared, C squared are of the same type. Also, the triples A, B, C, and 1 over B plus C, 1 over A plus C, 1 over A plus B are of the same type. But the triples A, B, C, and 1 over A, 1 over B, 1 over C are not of the same type. Indeed, taking reciprocals reverses the order, so the ranking pattern changes. Next, we introduce a convenient bracket notation. We write the bracket with top row a 1, a 2, a 3, and bottom row B1, B2, B3 equal to a 1 times B1 plus a 2 times B2 plus a 3 times B3. So this bracket means the sum of the products of vertically aligned entries. Now comes the key theorem. If the triples A1, A2, A3, and B1, B2, B3 are of the same type, then the similarly ordered arrangement gives the largest sum S, which equals the bracket with top row A1, A2, A3, and bottom row B1, B2, B3. This is greater than or equal to the bracket with top row A1, A2, A3, and bottom row B1 prime, B2 prime, B3 prime. Here the second row is any permutation of B1, B2, B3. This bracket is greater than or equal to the bracket with top row A1, A2, A3, and bottom row B3, B2, B1 equal to lowercase s. This is the rearrangement principle for these triples. Note that same order gives the largest paired sum. Reverse order gives the smallest sum. That is the heart of the proof. Let us prove the inequality a cubed plus b cubed plus c cubed is greater than or equal to a squared b plus b squared c plus c squared a. Assume that a is less than or equal to b, and b is less than or equal to c. Then a squared is less than or equal to b squared, and b squared is less than or equal to c squared. So the triples a, b, c, and a squared, b squared, c squared are of the same type. Therefore, by the theorem, the bracket with top row A, B, C, and bottom row are squared, B squared, C squared is greater than or equal to the bracket with top row A, B, C, and bottom row C squared, A squared, B squared. Expanding this gives exactly a cubed plus b cubed plus c cubed is greater than or equal to a squared b plus b squared c plus c squared a. Equality holds only when a equals b equals c. This completes the proof. Here you can see a visualization of the inequality when A equals 1, B equals 1.5, and C equals 2. On the first number line, the value of the left-hand side of the inequality and the intermediate calculations are shown. On the second number line, the value of the right-hand side of the inequality and the intermediate calculations are shown. On the left side, we get 12.375, and on the right side, we get 10, which is obviously less than the left side. Next, we prove several elegant inequalities using the same idea, rearrangement. We compare ordered triples, build bracket expressions, and use permutations to obtain sharp lower and upper bounds. The key principle is simple: matching the same order gives the largest sum, while reversing the order gives the smallest. Example 2. We shall prove that A over B plus C over C plus A plus C over A plus B is greater than or equal to 3/2 for positive A, B, and C. The inequality we are proving is equivalent to the one shown at the top. In this form, it is clear that the numerator is non-negative and the denominator is positive whenever A, B, and C are positive. Therefore, the inequality holds for all such values, and its solution set is represented by the red-marked region in the picture. Since the triples A, B, C, and 1 over B plus C, 1 over C plus A, 1 over A plus B are of the same type, we obtain two rearrangement inequalities 2.3 and 2.4. Then we add them. Adding the two inequalities gives 2 times the sum is at least 3. Therefore, the sum on the left-hand side of inequality 2.6 is at least 3/2. Equality is possible only when A equals B equals C. The proof is finished. Example 3. We shall prove the inequality 3.1. If A is less than or equal to B and B is less than or equal to C, then A squared, B squared, C squared are increasing, and 1 over B plus C, 1 over A plus C, 1 over A plus B are also increasing. So the two triples given in equation 3.3 are of the same type. Therefore we get two rearrangement inequalities 3.4 and 3.5. After adding them, we obtain a lower bound in terms of A squared plus B squared over A plus B, B squared plus C squared over B plus C, and C squared plus A squared over C plus A, as stated in inequality 3.6. Each term on the right-hand side of the inequality 3.6 is at least 1/2 of the corresponding sums A plus B, B plus C, and C plus A, as given in formulas 3.7. So 2 times the cyclic sum is at least A plus B plus C. Hence the original sum is at least 1/2 times A plus B plus C, as written in inequality 3.8. Equality is possible only when A equals B equals C. The proof is complete. Do you know that elevators have signs saying no more than 8 persons or no more than 630 kilograms? These are inequalities. In fact, you can encounter inequalities in every area of real life. Now is time for example 4, which gives a double inequality. A plus B plus C is at most the quadratic cyclic expression, and that is at most the cubic cyclic expression. For part A, if A is less than or equal to B and B is less than or equal to C, then A squared, B squared, C squared, and 1 over C, 1 over B, 1 over A are increasing. So the aligned bracket sum is minimal, as is given in expressions for 0.3 and 4.4. Adding these inequalities gives A plus B plus C is at most 1/2 times A squared plus B squared over C, plus B squared plus C squared over A, plus C squared plus A squared over B. Thus, the first inequality is proved. For part B, the triples are cubed, B cubed, C cubed, and A over ABC, B over ABC, C over ABC are of the same type. Again, adding two rearrangement inequalities for 0.6 and 4.7 that follow from inequalities for 0.5 shows that the cubic cyclic expression is at least the quadratic cyclic expression. This completes the proof. Example 5. We shall prove that xy over z plus yz over x plus xz over y is greater than or equal to x plus y plus z if x, y, and z are positive numbers. If x is less than or equal to y and y is less than or equal to z, then 1 over z, 1 over y, 1 over x are increasing, and xy, xz, yz are also increasing. So rearrangement inequality 5.3 directly gives the desired inequality. Equality holds only when x equals y equals z. This concludes the proof. And now, dear viewers, I have a small homework task for you. Prove this inequality using the non-traditional method presented here for all positive A, B, and C. And let me know in the comments how it went. That is all for today. Please write in the comments whether you would like a continuation of this topic, for example the general case when inequalities involve n variables. Thanks for watching. If you enjoyed this video, please give it a like, subscribe, leave a comment, and share it. Thank you, and stay tuned for another interesting video coming soon.